Alright, try to break it into many different parts so that way you don't have to sit a long time and I will record a long video. Alright, this is the second part of your plane curvilinear motion. Okay. Alright, acceleration. So how are we going to get the acceleration? Here in this motion, it's the same as your straight line. The only difference is that we're looking at the motion in two coordinates, right? Two coordinate x and y, system. So now we're going to quickly review. Your acceleration is going to be in the same direction as your vector, yeah? So this is your combined resultant vector. Don't forget we are in curvilinear motion, so therefore you have the x and y component, yeah? So therefore when you find the acceleration vector from the velocity, you're going to have the same two component, which is represented by x and then represented by y coordinate axis. Yeah, so you're going to have the acceleration on the x-axis with the direction. Again, this is just telling you we're studying the acceleration in the form of a unit vector. Yeah, and then here is going to be your magnitude of your acceleration in the y, and then the direction of that acceleration, yeah, which is the j. Again, our vector is a one unit vector. It's just an ideal situation, yeah, what it meant. Average, the same thing. Your average acceleration is the change in velocity, and then we are going to look at that motion, okay? And here is your velocity, that motion from here to here between 2 points for a time interval. Yeah, so therefore you have a change in time here and change in velocity right there to get acceleration. Yeah, instantaneous is happening at a point, so therefore you're going to have a little change in velocity and then a little change in time. Yeah, again, two different lines right there. And of course when you differentiate it, you will get d squared r divided by dt squared. I'm not going to go ahead and explain that again to you. You should know that by now from chapter 2. Yeah, go back to the slide and you're going to get it. Here is the magnitude, direction of your y, and that's your x. Yeah, we're dealing with the xy coordinate in two-dimensional plane. Of course, we're going to see a little problem here for your acceleration. So your car rounds a turn. Rounds a turn means it's going here. Yeah, there is a curve right there. So rounds a turn at a constant. It's going with a constant speed. Yeah, your magnitude of your velocity is your speed. So is the acceleration 0? Yeah, what's going on right there when we turn? Yeah, if we go with a constant speed, let's say 40 miles per hour, what's going on right there at the acceleration? Yeah, is it 0? No acceleration at all? Or is there some acceleration that the car and you are experiencing at that point? Definitely no, yeah, because you are, look at the, you have a change in velocity, you go with 40, and then as soon as you curve, already studied that in velocity section, when you change the path, from another path, there is velocity. If you have a velocity, you have a change in velocity because you have one point here, second point here, and then you go that way, your position changes, your velocity changes, yeah, and it is happening from here to here time interval, which is this guy, yeah. So therefore you do have an acceleration, yeah. So therefore acceleration is not 0. In problem solving, we are going to review the equation. So the very first equation for acceleration is already told you about that. Your average is, this is instantaneous, is a little dv divided by little dt. And then your velocity, yeah, little dr, and then divided by little dt. This is position, that is velocity. Yeah, change in position against change in time, your velocity. Change in velocity against change in time is your acceleration. You're going to combine that two and put them all together. Yeah, so when you combine that two, what you got is, okay, so if you combine it, you're going to get rid of the time right here. Yeah, and of course you have your a and you have your b, yeah, okay, like that. And your v is dr, so therefore you can be able to put that in together. Yeah, Okay, so I wrote it here for you, yeah? So combining, meaning like we'll put it together. So if we put A by V, you're going to get A is dV by dt, okay, times your V is going to come down here, yeah? So therefore dr over dt, because right now V is dr by dt. If I put the V down, like 1 by V, you're going to get dt by dt because you're putting this dt up and then putting this dr down, yeah? So therefore 1 by V, which is this guy, 1 by V is equal to dt by dr. So therefore when you see this, okay, in your mind, you're looking at this, yeah? A multiply by 1 by V. A is this, so dV by dt, 1 by V is dt by dr, okay? So that's what we call it, yeah? Combining the equation, you cancel, yeah, dt, and then you're going to put this to that side, and then you're going to put this to this side. So that's what you get, V dt and then A dr, yeah? That's your algebra. So make sure you review your mathematics. Of course, now we are going to integrate the previous, yeah, equations. Integration again is going backwards, yeah. Your differentiation is going forward. We start from position, velocity, acceleration. You can go acceleration to velocity by integrating, and you're going to integrate velocity, okay, and you're going to get the position. If you differentiate, you're going to get velocity. If you differentiate, you're going to get the acceleration. Now we're going backwards, yeah. Now our previous equation, yeah, which is this guy. Let's go back one slide so you can remember that. So ADR equal to V dV. I wrote it here for you, yeah. So acceleration dr equal to V dV, okay. And that is from this two equation, yeah. A dV by dt and V is dr by dt. We're going to write that down. Okay, now we got all the previous equations. So the very first one we're using this, yeah? When you integrate it, that's what we get. So if you integrate and then we're going to move that to here, yeah, you will have to integrate. If you integrate this side, you've got to integrate this side. So this is what we get, yeah? Integration of V. We're going to bring this to the other side, so dt, and we have to integrate the other side and then dr, yeah? Of course, another one, the same thing, we're going to integrate that, we're going to bring this thing to the other side, so that's what we get, yeah, integration A dt. If you integrate this side, you're going to have to integrate the other side to keep this equality, yeah, the same. So therefore, you integrate that and you get dv, yeah? And of course, we're going to do the last one, we're going to integrate this side, so therefore, you also have to integrate the other side, yeah? To not to disturb this balance in between the two sides of your mathematics formula. Okay, of course, in real world, these are physical things, by the way, right? It is defining the acceleration of an object in motion. Okay, so don't forget that. So therefore, if you look at the acceleration, yeah, and with respect to your location, yeah, that's the same value as you're looking at the velocity with respect to the change in that velocity, and that's what is talking about the motion, yeah, motion behavior of this object. All right, so make sure study to get the concept, you know, what's going on, and try to get the connection between the mathematics formula and the real world objects, yeah. Otherwise, otherwise, yes, you won't be really getting it. Yeah, it takes time to get all of this. All right, the next section, we will slowly move into the projectile motion. So we gotta know what is the projectile motion. Alright, so you gotta know what is the projectile. Yeah, it's very important because if your ambition is going to the space, yeah, direction, like working for the spaceship rockets company, NASA, SpaceX, etc., etc., you definitely need to master this projectile. Yeah. It's also in your engineering technology, by the way. Your field is a very, very good field. Our field is very good field, by the way. So anyway, field means study field, career field. Yes. That is my office. A boiling water in the back. Okay, there are a lot of sounds behind. Let me stop here for a while to clear the sounds in the back. Okay, that's stop. So anyway, so you have a particle. So this time our subject of interest, we are studying a particle, and that is going with an initial velocity. Yeah, so your initial velocity is given to you as v0, meaning like initial 0. Yeah, and then not the value. It means 0 is initial. Okay, so initial velocity. and then allowed to move through the air. So we're gonna move through the air into on its own, yeah, going on its own. So go bam, 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 and then bam, yeah, right here. And this is your projectile. So here is your projectile, the starting point, and go with the velocity, starting velocity, and then go all the way to the apex, okay, about that height, and then go down back again, and then ended up right here at C. Okay, so if you look at the start point and the end point on the location on the X is going to be this, and we call that the range of the projectile, yeah, is on X. And then of course the height of the projectile is on Y, and that is the highest point is B, okay, and that this is a distance of that, yeah, which you can be able to get from the Y coordinate axis number. Your range, you can get it from the X coordinate axis number. Your origin is 0, point, and where the projectile began, yeah, and here is your vector, yeah, velocity vector, and it has an I direction going that way to the positive direction on the X, Y direction going this way, the positive direction on the Y. So your direction going this and this, and this is your combined direction that you calculated from this triangle geometry right there. You know, use your you're going to calculate this hypotenuse, which is this long, yeah, side of the three-sided triangle. You can use these two sides, square them, add them, and get a square root, and you're going to get the value of that, okay. I would say like resultant, okay, vector direction going that way, yeah. And then of course the magnitude as well, yeah. With this velocity, the particle is going to go in this path, which is a projectile path, go all the way up, yeah, to the highest it can go, and that depends on the energy that it gets, yeah. Going from here, the motion depends on what the amount of energy it gets, and it's going to stop when that energy like is gone, yeah, when that energy is used up. So use up the energy and go up to that much and come back down and ended up at point C. Of course it won't come back to here because it isn't straight, okay, straight path going up and coming back down on a straight same straight path. This one is throwing, so therefore you're going to create a projectile curve like this and ended up a distance away from that starting point origin, okay. Because if we box it like this on this 2D plane space and we study with a fixed, yeah, Cartesian coordinate system, we're going to get this diagram, yeah. And of course we are going to neglect the environmental stuff, so we're going to neglect the air friction, which is your air resistance. So we're going to concentrate only the force acting on the particle, yeah, and then the particle weight. Of course there are only two things we consider in this, yeah, analysis. We're going to ignore everything else like the frictional force of the air, yeah, and to make it less complex in calculation, we're gonna just use the force, yeah, force that caused that motion, and then the weight of that, right, the particle. So you always have a mass if you have a body, which is this little particle, yeah. It doesn't have the size because it is a particle defined, yeah, very small, but of course it still has a weight, and your weight is, don't forget these things, yeah, mass and your acceleration. And your acceleration, again, we call it gravity, but it's your acceleration due to gravity pulling down towards the core of the earth, yeah. So this is your particle. So the only force acting on the particle is its weight, yeah, and we're neglecting the air resistance. And that is a projectile motion, yeah, starting point, ending point, take a height with the energy it got from the force that is used on that particle, yeah. And it is, of course, it also has a weight, so it's got to release the weight, otherwise it won't go, yeah, it will be whole at that point. So you need that force to overcome that weight, the gravity force, and then get to a certain point and then come back down. Since the particle motion is like that, you will definitely get a curved path, and that is your projectile, yeah, path, yes. You have a distinct starting point, a distinct ending point. you have a distinct velocity that it goes, which can be broken down in this Cartesian coordinate system into two components, yeah, one on the x-axis and one on the y-axis. The x-axis has a magnitude and also have a two distant direction going that way or that way. If you go that way positive, you go that way negative. Now it is going a positive direction. Your y-axis the same thing, going up the positive direction. Yeah, the combined direction is going to give you the direction of that particle. Yeah, and then the combined magnitude is going to give you the magnitude of that, yeah, particle. And the path is going to be this. Yeah, the height here you can get it from the y, yeah, coordinate system number. Your range is from the starting to the end position. You're going to get it from the x coordinate number of that Cartesian coordinate system. Yeah. So after a projectile, you gotta know falling. Falling is different from projectile. Yeah. So let's see what falling is. So we understand that all the objects that we know on this earth, okay, fall with a constant acceleration. Yeah. And of course, we have already studied, yeah, that constant acceleration is caused by the gravity. Gravity has a gravity constant, and gravity, even though we call it GGG, yeah, that is actually acceleration right there, going against with the mass, yeah, and that is actually a force right there, yeah, pulling towards the core of your earth, and we call this little g the acceleration of gravity, and that is your constant acceleration, and we got like 9.8. But you can also calculate with 10, and I don't mind, yeah? They're very close anyway. Alright, then what you need to know about in this example is asking you if the mass gonna influence a falling object, yeah? Falling object due to the gravity, yeah? Even though I write a G, that means a gravity force. So anyway, so does mass influence a falling object's velocity? So now we're gonna consider about the mass. So it doesn't, because velocity has nothing to do with your mass. So if you go into our mathematical formula, you're going to see acceleration. You got it by, this is instantaneous. So a little change in velocity divided by a little change in that time interval. Yeah, a little change mean this time interval is dt. So anyway, so when you think about it, yeah, and if you take the integration, yeah, by putting in this example scenario, because this example is we are dealing with the acceleration due to gravity. That is just a variable general equation. Now this is problem, yeah, so therefore we're going to put g as acceleration as a g. We're going to bring that thing to the other side, yeah, see, we're doing integration right now. So now you get the acceleration times delta t, okay. Small change, by the way, this t, this is a big change, yeah. So we have a acceleration due to gravity dealing with the time, okay, and I'm going to take the integration of that, yeah. And of course I have a g as negative because I am going, yeah, in y direction. We're going down, yeah, therefore you're going in the negative directions, therefore I put minus. This is showing you the negative. I'm going down, yeah, falling. It's a falling. Then if you take the integration on that side, we're going to take the integration on this side, yeah. So when you take the integration on this side, all we left is this dv, yeah. So that's a change in velocity, little change in velocity. So what are we doing this? We're trying to get the velocity. So if you integrate the differentiation, you're gonna get the pure velocity, yeah, the value of the pure velocity. If you do this a mathematical operation, so we operate integration on, okay, derivative, meaning like a little change. So this will be gone because of this operation. You're gonna left with the pure velocity, yeah. And then you do the same thing. We're gonna get rid of that, okay. You're gonna get a pure acceleration due to gravity, okay, times your time interval, which is t, yeah. Now right now it's not interval anymore because we get rid of this to get the pure value of that. So we get the simple value and direction is going down, yeah, because we're falling. So when you look at it, there is no place for mass. You know, mass is not included. So therefore, velocity, okay, is influenced by gravitational acceleration and time. That's it. It is not influenced by mass. Why? Because I don't see m in my equation. Yeah, so the answer is no. Okay, this is just a little cartoon so you understand, okay, what the resistance, what is the resistance generated by the air. Now, if you have an air mass, around your planet, so that air has a mass, so therefore it is going to give you resistance. Meaning like it has a mass, so therefore you need energy to go through that mass. So if you don't have a lot of energy, it's going to go through the mass of the air slowly. Meaning like if your mass of that particle is small, right? Of course, g is the same thing anyways. A g for the earth and g for the moon in this example. So it's just pulling, but then if your mass is so small, right, you don't have that much of force to go through the air. So if you think about a feather, it will go little by little. If you just drop a brick, it's going to go straight down because the mass of the brick is way bigger than the mass of the feather. So it has more energy because it's creating bigger force. Feather force is going to be small, so it's going to use a bigger force to go through the same air medium. So it's going to reach the earth fast. Bang. Of course, if you like let go of your feather on the moon, you have another story because the moon gravity, okay, is going to be different, from the earth gravity. Therefore, it will go really fast, okay, and there is no air, there is no atmosphere like our planet atmosphere. So therefore, your feather is going to go down really quick, like a brick on the moon. So that's just a little knowledge for you, so you understand the gravity, the air medium around your planet. When you don't have that medium, your the gravitational can be able to act on it, really fast. Another thing that you need to know about in this example is when you think about the size and shape of an object, which is in this example a car, the question asks you when would the size and shape of an object affect the speed, okay, speed at which an object falls, Okay, so here, and I would, I wouldn't use this example. Okay, car. I kind of when I look at it, it was like anyway. You can go back to the previous example, with the feather and the brake, of course. The mass example. Anyway, so in the second part of this example is like we're looking at the size and the shape of it. So the size and the shape. So of any of the object is going to affect the speed, okay, velocity, without the direction. So it's going to affect the speed when, you have this significant air resistance, So if you have like a significant air resistance, the size and the shape of any object that you're studying, analyzing its motion is gonna get affect. It's gonna affect especially the speed of it. The speed of that object falling towards the gravity. Okay, and you can never neglect that air resistance. And to here, I don't know why they put it. We can see it like it is going in like this kind of direction, and here of course there is your air resistance. So the size, the shape of that car is going to affect the speed, okay, of that car when you have this significant, okay, air resistance. So if you pay attention to the weather, if you have like heavy air, you're gonna have to use more energy to pass that air resistance or friction, okay, to make your motion. Alright, so what you gotta remember to solve your problem, by using the calculus in mathematics for the projectile, you've got to remember projectile problems, these equations, okay? Everything that I have already explained that to you. You have velocity component x, component y. To get the velocity, instead of r, we can also write just a regular x, refer to the x coordinate. Regular y refers to the y coordinate. Yeah. Acceleration, you're gonna differentiate velocity with respect to time. You will get acceleration. Yeah, you can find acceleration here, acceleration right there, and the combined acceleration. Okay, you can combine all of your equations all together and write it this way as well. Yeah, so it's up to you, whichever way that you want to do. Okay, here is just we are keeping this, yeah, like that, and we're keeping this like this, and we're writing that in this way. Okay, so if you put it over there to dt, yeah, you know that dt, yes, you can put it on that side, yeah, so you know that dt is a dy. Can be able to write it, okay, this way. I don't know if you can see it, yeah, here, yeah, when you look at this, we are putting that to the other side. We're putting this to the, yeah, other side, yeah, and of course see this, yeah, and see that, yeah, and we're defining this in the form of that, yeah. So if you put dt, I will get dy. I'm just moving that to there and bringing this to here, yeah, moving this to there. So that's dt, and then this one is a vy, yeah, and I'm gonna put that, yeah, into dt because I'm moving the dt to this side. So the dta times dt is, yeah, ay times dy by vy, yeah, right here. And then I'm going to move that vy to the other side, yeah. So that's what I'm doing. So when you study, make sure you write it in the way that I do, yeah. You're gonna have to write it down if you cannot be able to do it in your brain, okay. Moving equations. Since we do this 1,000 times, yeah, I have passed so many tests from bachelor degree, master's, PhD. So these are very easy for me, yeah, looking at it. Anyway, so and then we come back here. You can also, yeah, define your velocity, yes, with angle, and that would be polar coordinates, yeah. If you use a polar coordinate, we use the angle, yeah. So the angles are going to be defined with cosine and sine, yeah. The same thing, of course, your direction. We have a cosine theta in the x direction, and then sine theta is this going one direction. This is just a way of writing in polar coordinate axis, yeah. And so it's kind of like going from Cartesian xy, pure Cartesian xy, into polar with the theta, yeah, angle theta. Just a way to show the values of velocity. Yeah, here is we're dealing with this inertial velocity value can be calculated in this way. Cartesian, just x and y. Polar is going to be here, and this is the equivalent between value calculated by polar, and here is a value calculated by xy, yeah, coordinate system. They are slightly different, but it's still equal, yeah. Maybe like decimal point will be a little bit different. So anyway, so motion in the xy directions, again, they are independent. Therefore, you have x component and y component. In order for you to get a resultant combined, yeah, motion, you're gonna have to operate, each of the component and combine them. The next thing is we have a man and a woman here, yeah, and man is shooting with a gun, and woman is shooting with an arrow, yeah, and we're gonna compare. So we want to know like which one is gonna hit the ground first, yeah. Of course, we're not going to consider the air resistant in the atmosphere, yeah. So he is gonna shoot the bullet, and she is gonna shoot the arrow, and we have to identify which one is gonna hit the ground, yeah. Of course, the bullet is a little, yeah, particle, and your arrow is a very distinct, yeah, body with a particular shape, yeah, and size, yeah. So we have different size here and different shapes here, yeah. Of course, we're not dealing with the air resistant. We will neglect it. Since we neglect the air resistant, yeah, you will be dealing only with the falling acceleration, which is your g, they're gonna hit it, okay, at the same time. Yeah. Why? Because your size, and then your I would say size here, very difficult to write. Shape, okay, they affect the velocity only if you have the air resistance. Okay, so now we neglect the air resistance, so therefore your bullet and your arrow is gonna go straight down at the same rate. Okay, in the projectile problem, if you think about the x direction, if you don't have any kind of air resistance, your velocity in the x direction is constant. Okay, that's another thing that you need to know about your projectile problems. So you have your acceleration on the x-axis is 0 because our velocity is constant. Velocity can be calculated from differentiating the position. Okay, now position we usually write it this way. In polar we write it r, but in Cartesian we just go x. You can go x directly. Sometimes even in Cartesian we still write it r. So that's up to the person who calculate the problem. If you know that you're dealing with Cartesian, it doesn't really matter which symbol you use. You should know that your magnitude is going to be from the x-axis and y-axis numbers. And then your direction is going to be, it has only two directions anyway for each axis. Where is it going, up or right, left or down? Now, of course, we will get into a deeper math, and where we are breaking down, velocity in the x direction, and here is a position differentiation against time. We're gonna take integration because we wanna take integration on this side. You also have to take the integration on this side. We're just moving this. See this? We have a denominator and a numerator, and then we're gonna move to the other side. In review of your math, every time you have a fraction line, denominator is the one down, d for down. Okay, so denominator is going to be the number or the variable, all right, or the operation below the fraction line. This is your fraction line. Above is called numerator. Some student, younger student directly from high school, with very low level of mathematics, having an issue denominator and the numerator. So anyway, so you're taking the denominator to the other side. And then you integrate. If you integrate this side, you're going to integrate this side. While we're integrating, you can cancel the differentiation if you integrate in order for us to get the regular, vxt and x. So anyway, if you integrate on this side, you also integrate on that side. Now we're going to take this d out, and we will get the pure, vx0 t is equal to, okay, this is just telling you x, and x is going 0 all the way to x, so therefore that's your final and that's your initial. See that? Now we're putting the value into it. Of course, t is going 0 to 0 t to some t. So that's your time interval, so we don't really need to write that down because you have only one value, because the other one is 0 anyway. X, we have no idea what the values are because x0 wasn't defined. Sometimes it is 0 and sometimes there is a starting point, so therefore x minus x0. Okay, in this case I believe it's right here. So anyway, this one is if we bring the polar, which is your angle measurement, we can be able to relate the Cartesian x, xy with the polar. So this is where you can be able to see the angle. In terms of angle, we can be able to write your velocity in this way. So we're just trying to write this one. I'm just gonna circle it so you can see it. How easy that is. How do you get this? Is you're just moving that on the other side. So I have my x right here, and I am leaving this x and moving that to the other side. So if you move it to the other side, you got x0 plus the whole thing, and then I'm going to put this into the polar, by identifying with the theta. So if I put a Vx0, which is this guy, in a polar description, I get V is 0, and then times the angle. V0 means this line times the angle, and then times, which is your, this is a given t, okay? So velocity in terms of polar description is the magnitude of velocity times the angle in cosine. It is in cosine because of this triangle, triangle, just like that, okay? So therefore, when you deal the x, it's going to be cosine of that theta, yeah? And that's what we're talking about here. So make sure you review your sine theta or cosine theta from your mathematics, yeah? Don't make me teach everything. I have to teach the mathematics, I have to teach the physics, I have to teach the dynamics. Oh my gosh, and some students don't have any background. Then we do the same thing, yeah? On the y-axis, acceleration is constant. Yeah, and then of course we're going to neglect the air resistant, yeah? Acceleration is the differentiation of the velocity. Yes, right now we're concentrating the y-axis, okay? And your dv by dt is your acceleration, which is your gravity. And that is true for your projectile problem, yeah? Because your acceleration is nothing but going down gravity, yeah, which is gravity, acceleration due to gravity. That's the same. Okay, why? Because we differentiate the velocity, which is this guy, on the y-axis, yeah, in a time interval. Okay, so if you differentiate velocity, we're going forward direction. If you differentiate velocity, you will get the value of acceleration. Okay. In projectile, the acceleration is your acceleration due to gravity. Okay? Okay, so if your y, alright, coordinate axis right here, and the velocity, okay, on the y-axis, if that is not constant, you're gonna have a particular, okay, I would say like your gt, okay, is going to be your velocity, okay, initial velocity on that y, yeah, and then you have your final velocity on that y, and you're going to minus that, yeah. So this is telling you we're going to take the initial velocity out of final velocity, and you're going to get, yeah, acceleration and time, which is your velocity. So that is if your velocity is not constant. Your acceleration, you can get the acceleration by differentiating the velocity. We are dealing with the velocity on this axis, which is your y. So get the acceleration is happening only on that axis, yeah? And you will integrate that to get rid of this dt. If you integrate on this side, you're going to integrate on that side. The rest of them is just, plugging in ay. We're going to plug in with the minus g, yeah? And of course, when you get rid of the d with the integration, yeah, when you integrate the derivative, this is gone. And of course, your vy, we're going to put that in. So final minus initial, yeah, this is final, that's the initial. 0 is initial. You're going to end up getting, yeah, g and d, which is your velocity. Now we're going to write the velocity in terms of the angle, polar coordinates, yeah. Now our concentration is going to be on the y-axis, yeah. So therefore for y-axis, it is like that, okay, it's right here, this side. So therefore when you look at that, and that is a sine theta, yeah. So therefore you're going to have v0 sine theta, this guy, yeah, is this, okay, velocity of on the y-axis. All right. So these are when your velocity is not constant. This one is when the velocity is constant, yeah, acceleration is g. When the velocity is not constant, yeah, you will have a particular velocity on the y, and you use that into, yeah, here to get your acceleration, yeah. So that's little bit difficult for you. Again, I am not going to ask you to calculate, yeah? And I'm just asking you to at least know that if you go from position, yeah, to acceleration, you gotta go through velocity, and you will differentiate backwards. You're gonna integrate. All right, at least that one you gotta get it. Yeah, integration is here. If you want to get rid of this d, you're gonna integrate and it will dissolve. Yeah, like that. So now I want to get rid of dt. I integrate it, so I get a pure number right there. All right, the next one is again, we will go from velocity into position, yeah? So if you want to get the position on the y-axis, yeah, you can, of course, differentiate the y-axis and you will get the velocity. We do the change thing, again, the same thing. And you're going to end up getting, okay, getting the y position by using this equation, yeah, y0 plus v y0 t minus gt squared divided by 2, yeah? And if you want to write this in polar, yeah, which is this little guy right here, yeah, we do the same thing, yeah? And of course, that would be the sign because your concentration is right here, which is your y, yeah? This is again another rectangle which is parallel to each other, so you can use the same thing. Even though we are concentrating on the y-axis, that's parallel to that, so it's the same thing, yeah? So therefore, with this angle, yeah, theta, this side is your sine, yeah, b0 sine theta. If we want to calculate the side of that, yeah, so that's how we get it. Then your y, this is just a direction, so y direction velocity at the apex, so which is this guy, is 0, yeah? So we have just done 3 points. One is a constant, and second one is a change, and then the third one is the y, okay, direction velocity is now right here, yeah? So in that way, you don't have any more velocity because you depleted your energy, yeah? It can't go any more than this. So your motion, okay, has the particle without the velocity at the highest point, yeah? So now we study this point, we study the point in between, and we study the initial point right there, okay? All right. Then the next point to deal with the projectile problem is if your starting height of the projectile, yeah, is the same as the ending height, meaning we're going to start from the ground like that, yeah, because the ending height is right here, 0. So we're going to start with the 0. Then the motion of that projectile is completely symmetric, see? So this side and that side is completely symmetric. So this where if you start from the 0, because you ended up at 0, yeah, position on the y-axis, you're going to get a symmetric projectile, meaning it's a pretty projectile, yeah? Not like you starting from one point and going like that, yeah? There are many different projectiles, because if you go like this, you get a perfect symmetric projectile, yeah? So NASA and space, yeah, company, they always have to calculate that projectile because they're shooting a rocket, yeah, or satellite, and positioning that at a particular point, yeah. So that is how we how we calculate the path and the distance, yeah, of your predicted position that you want that to locate. Okay, so here, what is the x direction? So we're dealing with the x direction, acceleration of a projectile. So now we want to know the acceleration of that projectile. So we come into here, yeah. So if you think about the acceleration in the x direction, yeah, of the projectile, that would be 0, yeah, because you're going with a constant velocity, okay? So I show it right here for you, yeah, why the acceleration is 0. It is because in the x direction, your velocity is constant, yeah. Your dx divided by dt is going to have a constant, all right, velocity. So therefore there is no acceleration on x-axis. The y direction, which is this axis, y-axis, yeah, this velocity that we're talking about. So what is this velocity, yeah, at the apex of this trouble? So yeah, we got to understand that again. Of course, it's going to be zero because your energy, yeah, of the particle in the projectile motion will deplete it, meaning like zero energy to go further up. Yeah, so therefore here you're gonna have a velocity is completely zero. Yeah. What is the y direction acceleration of a projectile? Again, this is your y velocity. Yeah, we want to understand what's going on, acceleration at that time. Again, y is going against, yeah, the gravity, so therefore your gravity is always going down like that, so that's a negative g. Yeah, then of course we have to understand the velocity, yeah, in this y direction of the projectile. Something that is important is how you're going to calculate that. Yeah, you're going to calculate the y velocity on that y-axis, okay, in this way. Yeah, by using g, by using polar theta. If you're given only theta, we're going to use this equation. If you're given only velocity, time, and acceleration due to gravity, you use this. Okay, if you're given only y and t, you're going to differentiate it. Yeah, so that's calculus, that's sine and cosine. Okay, we go into this different calculation, or it's just a mathematics, different operations that we're doing to get the same velocity. Okay, it depends on what's given in your problem or what we know. So these are the given information. Yeah, if you just know the theta and you're not given the other aspect of it, like you don't know what y is, then you have to use this equation, of course. Yeah, if you know the y, then you use this equation. Yeah, if you don't know the angle and you know only the velocity and time, then you're going to use this equation to get the velocity on the y direction. Okay, so that's pretty simple as that. Alright, the next problem is looking at, you're going to imagine that you are a passenger in one of those very tall monster trucks. Yeah, so that truck is driving safely at a constant speed down a long straight flat highway. Yeah, so these are the thing. Again, draw the diagram. Yeah, so imagine that you have a ball in that situation, and then you're gonna roll it down the truck window. Yeah, and drop the ball outside of the truck. So basically, you're dropping a ball, right, from your window of the truck. And then neglecting, we're not going to consider the resistance, so we don't care about the shape and size of it. Yeah, and meaning like your g is the same. Yeah, so now how does the ball behave before it hits the ground, right? So now you gotta understand. You're given different situations here, and you're gonna choose one of them. The very first one is the truck. Quick passes the ball up. The truck and the ball and the truck travel side by side and remain even. The ball passes the truck. The ball passes the truck briefly and then starts to lag behind. Not enough information. So what is it? You have to think about it. You're dropping a ball through the out of the window, driving in a truck. Yeah. So what would the ball motion is going to be? So that's what you are thinking. Yeah, of course. The most important thing is there is no air resistance. Yeah, if you don't have air resistance, what's going to happen is you won't have your velocity is not going to get affected. Okay, it's not going to get affected, and that is the main point of it. Now, without the air resistance, nothing is causing the ball to slow down in that direction it's traveling. So therefore, your ball and the truck is going to travel side by side and remain even. Isn't that so weird? Yeah. If you take away the air out of our Earth, everything that you drop will travel with you because your velocity is not get affected, yeah, by your size and the shape. Okay. All right, then we're gonna put the air back into the same problem. So if we have the air resisting, what is gonna happen? So you gotta think about the size and you have to think about the shape. Yeah. So what's going to happen is the size of the ball is smaller than your truck. Of course, your truck also have the energy because you're driving. The ball doesn't have a lot of energy because you're dropping the ball. So the only energy is God, yeah, is the energy transfer from your hand and its own energy, which is the force coming out from the mass of the ball and the acceleration due to gravity pulling it down towards the core of the earth, yeah. So therefore, your ball is going to slow down, yeah, and of course your truck is going to keep going with its own, yeah, energy at its own, constant speed. Okay, so the truck is going to quickly quickly pass the ball, yeah, the ball will lag behind. All right, so the next situation in this problem is how would you answer change if at the moment the ball was dropped? So now we are going to think about the instant, yeah, and that instant is the ball was just dropped, yeah, and because it said it, so at the moment the ball was dropped, so the driver releases the gas pedal, bang, and then the truck starts to coast, and we are not going to neglect the air resistance, yeah. And here in this problem is when you think about it, it's not just only the ball drop at that moment, yeah. We are in a very complex situation here. One is at the moment, okay, that's one issue. Ball drop, second issue, the driver released that gas pedal, that's going to affect both of the motion of the car, or I mean the truck, and the ball, yeah. And then the truck starts to coast, and the truck itself is changing, path. So that's a lot of like 1, 2, 3, 4, and air resistance. So 5 things you have to consider. So too complex of a problem right there, yeah. So therefore, this all of this cannot happen because we don't have enough information to solve that problem, yeah, at all, because you have too many things going on at the same time, yeah. So therefore it's a complex problem, and you're going to need, more information to accurately, yes, calculate and solve this problem. So the truck has a higher drag, coefficient. That's just a mathematical constant that we have to use um, in this situation, because we're comparing the truck and the ball, and then of course your drag coefficient is important, and then your truck weight is important, your truck inertia, because air resistance is there for us to consider. So does your balls, inertia, because air resistance is affecting both of them, and then they also requires a large force, right, to slow, because the truck is coasting. So all of that, we cannot be able to solve this problem because we don't have enough information. Yeah, that's the problem, the situation, or the activity. That we want to analyze is too complex. You're gonna need a computation or program to calculate and analyze this kind of mechanical dynamic problem. Alright, now you're going to drop the object, and we know that its acceleration, we're on the earth, so it's going to be g, going down, yeah? So, meaning like going a negative g. So what happens if with all you might, you throw an object up? So now we're going to throw it against, of course, every time you throw something, you have to transfer your energy. Without the energy, it won't go up, against the gravity and then the air, if we consider the area. So what's the object acceleration after you let go of it? So we want to know the object acceleration after you let it go from your hand, throw into the air, that would be equal to g, why? Because you have to overcome that pulling, gravity with negative, mean it's just a direction going down, because there is this, right, gravity force pulling down the ball, okay, with gravitational acceleration g, so that what you need to overcome this thing. In order for you to overcome, you got to get like you got to get the object the same acceleration, which is g, and of course in a opposite direction, because you're pulling is down. If we want to go up, that's the opposite direction. yeah, and you have to give the same magnitude of g to let it go, yeah, otherwise motion will not happen, yeah, so therefore the answer is equal to g. Now you're going to imagine that you and a buddy are standing next to each other holding baseballs. Your buddy throws his baseball up with an initial velocity of 30 miles per hour, and you throw your baseball down with an initial velocity of 30 miles per hour from the same initial height. So neglecting air resistance, this time we're not going to consider air resistance in this problem, and which ball hits the ground with greater speed. Okay, and we gotta determine which ball is gonna hit the ground with a greater speed. So your buddy throw up, you throw down. You both use 30 miles per hour speed initial. Yeah, this is initial. And we want to know which one hits the ground with a greater speed. So it's going to be with the same speed. Why? Is because the question is asking you only, yeah, let me go back here to this, okay? It's just asking you, all right, which ball hits the ground with a greater speed. So we're concentrating only on the speed, okay? So if you concentrate only on the velocity, the only thing that your velocity depends on whether you throw up or down, okay? In order for the ball to hit the ground, this one throw up and come back down, this one throw straight down, okay? And we are considering the speed, which is the magnitude of your velocity, because velocity has a direction. So that speed, okay, hitting here is going to be the same. Why? Because your velocity depends on what? Yeah, your velocity always depends on the change in position over time, yeah. And for this case, we're dealing with the gravity, and it's going to pull you with the same gravitational energy, okay. And if you just want to get the velocity, pure velocity, all you do is integrate that, yeah. So we're getting like this, by the way. So you gotta have this in your mind, okay? So instead of going from the position to velocity, we are using the g, the same g, to get velocity by integrating it in our mathematics. So you are going to hit with the same speed. Why? Because you have the same, yeah, the same acceleration due to gravity. Yeah. So the questions only ask you the magnitude. It said it's so speed. Doesn't say anything about the direction because speed is a scalar. Yeah. So therefore we want the pure velocity magnitude. So therefore you have to integrate the acceleration. And that acceleration is the same. So therefore you're gonna have the same speed. Okay. Alright, so for your course, the anti-coordinate is not included. Okay, so that's a part 2 of the dynamics. So yours only part 1. So therefore, we are not doing this at all. Okay, so you will stop right here at the example problem after you finish. Yeah, before we get into the anti-coordinate, which is the part 2. So you are required to do only the part 1, yes, of this chapter 3 for this course, yeah, in your curriculum. This is too complex for you, but I will provide the handout, yeah, for those who want to go, yes, to RIT. If I do have some time, I will make lectures and put this for you as an extra, yeah. But if I don't have time, I'm not going to do it, yeah. And whenever I have summer, if I have extra time, I will put that into the same playlist for you, yeah. If you do wanna do it on 4 hour, yes, this dynamic 2 or 8 course at your level for the freshmen, yeah. These are freshmen and sophomore, right? Even though what age you are in, I know that some of the students are older, but you still is in the freshman and sophomore, yeah, level of education. So therefore, yes, we are going to cover only the part 1 of the dynamics. Yeah, part 2 is actually the second semester we usually do that. Yeah, because we have dynamics 1, 2, and 3 for. I don't know how RIT is doing. Anyway, so I study 1, 2, and 3. Yeah. Of course, in PhD there's 4, but we heavily use the computational, programming like Python or MATLAB, etc., etc. Yeah. So anyway, so let's stop right here. So all you have to do is the part 1. Yeah. I can go back to show you and stop right here at the example problem. Calculation is not included. Yeah. So we do only of course kinematics, from here, and go all the way to, what was the page number, I forgot. Now we're gonna stop right before this anti coordinate. So chapter 3, before anti coordinate, you're going to stop. So we won't go into the particle kinematics in part 2. Of course, if you scroll down the handout, you're gonna see a lot of heavy mathematics, but we try to make it in this digital textbook, interactive textbook they do. Of course, you will go into the circular motion. It's very interesting because these are real life motion, and see like how complex it is. To calculate according to the path that your particle object is taking. Here again, we go into the polar coordinates. That I wanted to cover, but then the department doesn't approve. So it just if you are interested, you're welcome to read this. If I have time, I will. Put up the lecture on it when I have time. And this is where we study. I'm just showing you. See, there's a robotic arm. So it's very, very important. And that can only be determined by the polar. So anyways, if you want to go into the robotic direction, you gotta do this. And anti-polar, and you have to understand the difference between them. Right now in this course, and you don't need it. Yes. And the next section is just choosing the right coordinate system. Of course, and we study only the Cartesian coordinate, and we don't study polar coordinates, and the other one is anti-coordinates. So you don't have to do this. Choosing the right coordinate system to solve a different complex motion. So here where our rocket, these are very, very interesting. Your tank here. I'm just showing you what's in this, and then of course we go into the relative motion. Relative motion is another thing very important, because we are studying not only a particular object with a particular path, but we're studying the object, and then you have another object, and they both are in motion. So that's where the relative motions come in, and reference frame is very, very important. Because you will be studying the 2 objects in motion, and then try to understand how each motion is affecting the other one. Since we have a relative motion, we have relative position. So that go all the way down, relative velocity, acceleration. And then it's gonna go straight down to the constraint and dependent motion. These are level 3 to 4, by the way. But of course, we make it pretty easy, because this entire textbook is used in dynamic 1, 2, and 3, for 4-year engineering and engineering technology courses. Use the same textbook. So anyways, if you do want to study the entire thing, make sure, of course, it's interactive, so there's videos and everything are in it. You can be able to study all the way to the end of this. But of course, for this class, it isn't necessary. So they eliminated many of the stuff that you need. I personally don't want you to but anyway, I understand that your mathematics is not very, very strong. So we don't have to go into the giants and stuff like that. Anyways, I just show you like what's in it. If you have interest, make sure that you go. For this class, we only need the very first few sections, which I have already covered for you. That's it for today. And again, please just study up to NT, before the NT coordinate, and cut there. Your quiz is gonna cover only up to there.